Welcome to the deep dive. Today we're really diving in, gearing up for what feels like prepping for a big test on computer fundamentals.
That's a good way to put it.
We're tackling multiplication, division, algorithms, and the concept of pipelining in processors.
Yep, we've got that source doc, the COA M3 PDF, and the mission today is simple.
hmm
Extract the key stuff, make it clear, make it stick.
Like creating the ultimate study guide right here.
Exactly. By the end, you should feel pretty solid on these topics.
Okay, yeah, some of these terms, arithmetic, algorithms, pipelining, they can sound a bit heavy.
They can, but we'll break it down. Think of it step by step.
Your expert study partners, ready to go.
Let's do it. Where should we start? Multiplication.
Yeah, let's start there. Multiplication. Fundamentally, what is it in binary terms?
Well, at its core, it's surprisingly familiar. It's basically adding shifted versions of the number you're multiplying, the multiplicand.
Just like long multiplication we learned in school, right? You shift things over.
Precisely. The source uses 13 times 11 as an example. That's 1101 times 1011 in binary.
Okay.
For every one bit in the multiplier, 1011, you take the multiplicand, 1101, shift it left according to the position of that one, and then you sum up all those shifted versions.
So you generate these things called partial products.
Exactly. And adding them up gives you the final answer.
Okay, that makes sense. Now, how does a computer actually do that? The source mentions the array multiplier.
Ah, right. This is a hardware approach. Imagine a grid, like a 2D array of logic components.
A combinational array, it says.
Yes. At each point in this grid, you basically have a full adder and an A&D gate working together.
Okay, an adder and an A&D gate, what did they do?
The A&D gate is controlled by a bit from the multiplier. Let's say you're looking at multiplier bit key and multiplicand bit min-j. The A&D gate takes both. If key is 1, the millibit bit passes through to the adder.
And if key is 0?
Then the A&D gate outputs 0. So effectively, you're either adding a bit of the multiplicand or adding 0, based on the multiplier bit.
Got it. So each row in this grid adds a potentially shifted version of the multiplicand.
Exactly. Each row adds the correctly shifted multiplicand, if the corresponding multiplier bit is 1, to the partial product coming down from the row above it.
The source mentions PP0 starting at 0.
Right, the first partial product input is 0. And as you go down the rows, say to PP4 for 4-bit numbers, you've accumulated the final result.
And the shifting. How does the array handle the left shift for each partial product?
That's done by how the signals are routed. They travel diagonally down through the array, effectively shifting the bits to the left relative to the partial product coming in from above. It's quite neat.
It sounds very direct, like mapping the paper method straight to hardware, but there must be downsides.
Oh, definitely. And this is important stuff for understanding the trade-offs. First, the sheer amount of hardware.
Yeah, it says n squared A&D gates for n-dit numbers. That sounds like a lot.
It is. And then you have the adders. The source specifies n times, n2, full adders, and n half adders. Remember, a full adder needs 3 inputs, 2 bits plus a carry-in. A half adder just takes 2 bits.
So many, many components, which means more chip area, more power.
Precisely. Not great for, say, mobile devices. And the other big issue is speed.
A critical path.
Exactly. The longest path a signal has to travel through this array of gates determines the overall multiplication time. And in an array multiplier, that path can be quite long, potentially going through n adders in one row and 1 in another.
Adding up delay at each stage, so it might not be as fast as it first appears, especially for larger numbers.
Right. The complexity scales up and the delay increases, which leads us to the alternative.
The sequential circuit multiplier.
Yes. This takes a different approach. Instead of doing everything at once with a huge array, it does it step by step, reusing a single adder.
Okay, so less hardware, but it takes more time.
Generally, yes. It uses one n-bit adder, but it uses it n times, over n clock cycles.
How's it set up? The source mentions registers A, Q, and M.
Right. M holds the multiplicand that stays put. Q starts with the multiplier. A is the accumulator, initially 0, where the partial product builds up.
And there's a flip-flop C for carryout?
Yep, catches any carry from the addition. And critically, there's a MUX, a multiplexer.
What does the MUX do?
It decides what gets added to A. Look at the least significant bit of Q, let's call it Q0. If Q0 is 1, the MUX selects the multiplicand M to be added to A.
And if Q0 is 0?
If Q0 is 0, the MUX selects 0. So essentially, no addition happens in that cycle, just like in the paper method when the multiplier digit is 0.
Okay, so add or no add based on the multiplier bit, then what?
After the potential addition, the combined registers C, A, and Q are shifted right by 1 bit.
Ah, a right shift. Why right?
It serves 2 purposes. It shifts the partial product that's forming an A to the right, And crucially, it shifts the multiplier in Q, so the next bit of the multiplier moves into the Q0 position, ready for the next cycle.
And the bit that falls off the right end of A goes into the left end of Q.
Well, the carry C shifts into the leftmost bit of A shifts right, and the rightmost bit of A shifts into the leftmost bit of Q. Q shifts right, and it's LSB Q0 is the one we just used.
Okay, I think I follow the flow. Load M and Q, clear A and C, then repeat N times, check Q0, maybe add M to A, then shift CAQ right.
That's the algorithm. The final product ends up spread across registers A and Q after N cycles. Less hardware, but it takes those N cycles. A clear trade-off.
Okay, that covers unsigned numbers pretty well. But computers deal with negative numbers too, usually with 2's complement. How does that change multiplication?
Good question. The main complication is handling the sign, especially when multiplying a negative number. This introduces sign extension.
Can extension. What does that mean exactly?
When you're adding the partial products, you need to make sure you preserve the sign of the intermediate results. If a partial product represents a negative value, in 2's complement, its most significant bit, MSB, is 1. When you shift it left before adding, you need to fill the new space on the left with 1s, not zeros.
Ah, so you extend the sign bit. If the MSB is 1, pad with 1s. If it's 0, pad with 0.
Exactly. The source shows negative 13 times plus 11 using 5 bits. Negative 13 is a 0, 0, 11. When you generate partial products using the bits of plus 11, 0, 1, 0, 11, those partial products based on 1, 0, 11 need to be sign extended to the full width of the final product, which would be 10 bits here, before adding.
That ensures the negative values stay negative as they get shifted and added.
Precisely. It maintains the correct 2's complement representation.
The source also mentions a trick if the multiplier is negative.
Yeah, instead of dealing with sign extension complexity caused by a negative multiplier in some algorithms, you can take the 2's complement of both the multiplier and the multiplicand.
So flip the signs of both numbers.
Right. Then multiply them as if they were positive using a standard unsigned algorithm. The result's magnitude will be correct. And since you flip both signs, the overall sign of the product is also correct.
That's neat, a good shortcut to remember. And just quickly, 2's complement. MSB 0 is positive, MSB 1 is negative.
Correct. Now, building on sign multiplication, there's a more sophisticated algorithm called the Booth algorithm.
Booths. Sounds important. Is it faster?
It can be, especially in certain cases. It's designed specifically for sign 2's complement multiplication and handles negative numbers elegantly. It works by looking at pairs of bits in the multiplier.
Okay, how does it start? What's the setup?
You load the multiplicand into a register, BR. The multiplier goes into QR. You need an accumulator, AC initialized to 0, and one extra bit, QN plus 1, also set to 0 initially.
BR, QR, AC, QN plus 1. Anything else?
Yes, a sequence counter, ASC, set to N, the number of bits.
Got it. So what's the core logic? Looking at pairs of bits.
Right. In each cycle, you look at the last bit of the multiplier, QN, the LSB of QR, and the extra bit, QN plus 1. You compare this pair.
Okay.
If you see AO1, meaning QN is 1, QN plus 1 is 0, you add the multiplicand BR to the accumulator AC.
OO1 add BR. Makes sense.
If you see 10, QN is 0, QN plus 1 is 1, you subtract BR from AC. That's usually done by adding the 2's complement of BR, which is BR plus 1.
10 subtract BR. Okay, what about 0 or 11?
If the pair is 0, 0, 11, you do nothing to AC in this step. No addition or subtraction.
Interesting. So action only on transitions between 0 and 1.
Potentially, yes. After that potential add, subtract, nothing step, you perform an arithmetic shift, right? ASHR, on the combined AC and QR registers.
Arithmetic shift. Why arithmetic?
Crucial point. An arithmetic shift preserves the sign bit, the MSB. When you shift right, the MSB is copied into the new MSB position, maintaining the sign.
Okay, so ASHR, AC, QR, then what?
Then you decrement the sequence counter SC, and you repeat this whole process, compare QN, QN plus 1, operate on AC, ASHR, AC, and QR, decrement SC until SC hits 0.
And the final result?
It's contained in the combined AC and QR registers.
The source has examples like -9 times -13. Working through those seems key.
Absolutely essential. Let's quickly trace that one. 5 bits, -9 is 1111 BR, -13 is a 1111 QR, AC 00000, QN plus 1, S equals 5.
Okay, cycle 1, QN1, QN plus 1, 0, that's 10.
Right. So subtract BR from AC. AC plus, negatives AC plus, negatives BR, what is 00000, plus 2's comp of 10000 plus 01001 exceeds 0101
then ASHR, AC, QR. So AC becomes 0, 0, 100, QR becomes 11, 0, and 1, and that last one from QR becomes the new QM plus 1.
Okay. Cycle 2, QN1, QN plus 1, 11, do nothing. AC 0, 0, 0, 1, QR 0, 100, QN plus 1, 1, SC3.
Right, QN 0, QN plus 1 type. Subtract BR again. AC 0, 0, 0, 1, 0, 0, 1, ASHR, AC 0, 1, 1, 0, 1, Q1 plus 1, 0, QN plus 1, 0.
Cycle 4, QN 0, QN plus 1, 0, 0, 0, do nothing. ASHR, AC 0, 1, 0, 1, QR 1, 1, 0, 1, QN 1, 1, 1, and QN plus 1, 0, 10.
Cycle 4, QS 0, 1 plus 1, 0, 1. There you go. See, AC 0, 0, 0, 0, 1, 0, 1, QR 1, 1, 11, QN 1, 1, 0, 1, QN plus 1, 0, 10. SC 0. Subtract BR. AC 0, 0, 0, 1, 1, adding 0, 1, 0, 1, 1, and QR 1, 1, 1, QN plus 1, 1, SC 0. Stop.
Wait, let's recheck cycle 5 subtraction. AC was 0, 0, 0, 0, was 0, 1, adding 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, and 1. Okay, and ASHR gives AC 0, 0, 0, 0, 1, 0, 1, 0, and we will AC 0, 0, 0, 0, 1, 1, Q1 1, 1, 0, 1, Q1 1, 0, 1, SC 0, 1, 1, 1 plus 1, 1, 1, Q1 plus 1, 1, SC4. Looks right so far.
Cycle 2.
QN 1, QN plus 1, 11, no put. ASHR, may 0, 0, 0, 0, 0, 1, QR 1, 1, 0, 1, 1 plus 1, SC3. Say 4, says 0, 1, 1, SC3. Still okay.
Cycle 3, QN 0, Q1 plus 1, 1, 10. Subtract BR, ACC 1 plus 0, 1, 0, 1 plus 0, 0, 1, 0, 1, 0, 1, 1, ACHR, SC 0, 0, 0, 11, QR 1, 1, 0, 1, 0, 1, 0, 1, 2, plus 1 plus 1, 0, 30. Cycle 4, QN 0, Q1 plus 1, 0, 0. No, ACHR 0, 1, 0, 0, QR 1, 1, 0, 1, 0, 1 plus 1 plus 1, 0. Okay. Cycle 5, Q1 plus 1, 0, 2. Subtract BR. Subtract BR. 0, 0, 0, 0, 0, 0, 0, plus 0, 0, 0, 0, 0, 1, 0, 0, 0, and AC 0, 0, 0, 0, 0, 0, AC 0, 0, 0, 0, Q1 plus 1, 0, 0, S. I mean, it's 0, 1, 0, 1, 0, check the source.
Source cycle 5. QN1, QN plus 1, 0, 0, 10. AZM plus 0, 0, 0, 0, 1 plus 0, 1, 0, 1, 0, 1. AZ 0, 0, 0, 0, 1, 0, 1. QR 1, 1, 0, 1. QM plus 1, 0, 1. The source text says the result is 0, 0, 0, 0, 0, 1, 1, 0, 1. But their trace seems to yield 0, 0, 1, 0, 1, what we did. Let's trust the algorithm logic we followed. The key is the process.
Right, the process.
Yeah.
Check the pair, add, subtract, none, ASHR. The other examples, like 13 x to 6 or NAC and 11 by 8, follow the same pattern. And if the expected result is negative, the final ACQR will be its 2's complement representation.
Exactly. And this concept of looking at transitions relates to booth recording. Scanning the multiplier right to left with an implied 0 at the very right. Going from 0 to 1 means start a block of 1s, subtract multiplicand. Going from 1 to 0 means end a block of 1s, add multiplicand.
So it effectively encodes the multiplier based on these transitions.
Yes, and this explains its efficiency. The worst case is alternating 0s and 1s, like 0, 1, 0, 1's y, which causes an operation every cycle.
But the best case?
Long strings of 1s, like 0, 0, 1, 1, or 1 and 0. Standard multiplication would add 5 times. Booth sees 0 to 1 at the right, subtract, then 1 to 0 at the left, and just shifts in between. Much faster for blocks of 1s.
So average speed might be similar to normal multiplication, but it shines with certain patterns in the multiplier.
Precisely. It's a clever optimization for signed numbers.
Okay, multiplication mastered. Let's switch gears to integer division.
The inverse operation. The source helpfully compares it to decimal long division first, like 274 divided by 13 on paper.
Right, you see how many times 13 goes into 27, right, multiply 2 by 13, 26, subtract, bring down the 4, see how many times 13 goes into 14, right, 1, multiply 1 by 13, 13, subtract.
It's the same logic in binary, but simpler, because the quotient digit can only be 0 or 1. Does the divisor fit or not?
And the main algorithm presented is restoring division. The name sounds restorative.
It does, because sometimes you have to restore the value after a trial subtraction.
How does it work?
You position the divisor relative to the dividend. Then you try subtracting the divisor.
Okay, subtract. What then?
If the result, the remainder, is 0 or positive, great. The divisor fit. The quotient bit for this step is 1. You then shift things for the next step.
But if the result is negative...
If it's negative, the divisor didn't fit. The quotient bit is 0. And here's the key. Because the subtraction failed, you have to add the divisor back to restore the previous value before you shift and continue.
Hence restoring. You undo the failed subtraction.
Exactly. The hardware setup usually involves register M for the divisor, Q initially holding the dividend, and A starting at 0. A accumulates the remainder, and Q gets shifted left, gradually filling up with quotient bits from the right.
And the algorithm runs n times for n-bit numbers.
Yes. Each iteration involves
1.
shift A and Q left together by 1 bit. This effectively brings the next dividend bit into play and makes space for the next quotient bit.
2.
Subtract M divisor from A, AM. Remember, this is usually done using 2's complement. A plus M plus 1.
3.
Check the sign bit of A. If it's 1, negative result.
Then the subtraction failed. Set the new LSB of Q, which is Q is 0, 0, and restore A by adding M back. A equal A plus M.
Correct. But if the sign bit of A is 0, positive or 0 result.
Subtraction succeeded. Set Q to 1, and crucially, don't restore A. Keep the result of the subtraction.
That's the whole loop. Repeat n times.
The example, dividend 8 1000, divisor equals 30011. Using 4 bits for simplicity, though the source might use n plus 1 bits in AM for sign handling.
Right. Let's trace it quickly, assuming A is also 4 bits, initially 0000.
Initial, A 00000000.
Initial, A000, Q1000, M0000.
Cycle 1. Shift AQ. Left 0000. Subtract MA 00000000. A equals 00000000. A 0000000000. Subtract MA as 000000000000000000. And M is plus 00000000.
Cycle 3. Shift AQ left A00000. Subtract M, A00000000001 plus 11 1 plus 11 1. And sign 00 positive. Ignore carry out for this check.
Success.
Yeah.
Set Q001. Q becomes 0000. Don't restore A. Keep A0001.
Cycle 4. Shift A, Q left A00001. Q0001. Subtract M. A equals 00100001 plus 110001 to 001. Sign 1.
Set Q00. Q becomes 00010. Restore A. A equals 00010 plus 0010. End of 4 cycles. Final state. A remainder equals 0010 decimal 2. Q quotient equals 00010 decimal 2, which is correct. 8, 3 through goes 2, remainder 2.
Perfect. It's methodical, if a bit complex with the restoring step.
It is. It forms the basis, though. Okay, arithmetic done. Ready for speed? Let's talk pipelining.
Yes, this is how processors get things done fast, right? Like an assembly line.
Exactly the right analogy. Instead of one unit doing an entire task start to finish, you break the task into sequential steps and create a dedicated hardware segment or stage for each step.
So instructions flow through these stages.
Right. As one instruction finishes stage 1 and moves to stage 2, the next instruction can enter stage 1.
The source uses fetch, F, decode D, execute E, write W is a classic example.
A very common model. While instruction 4 is being fetched, instruction 3 could be decoded, instruction 2 executed, and instruction 1 written back. Multiple instructions are making progress simultaneously. Needs separate hardware for each stage and buffers between them.
Definitely. Each stage needs its own logic circuits, and you need registers between stages to hold the data and control signals as they pass from one stage to the next, synchronized by a clock.
Okay, so this pipeline organization, input register, then combinational logic circuit for the subtask.
That's the typical structure for each segment. Data clocked into the input register, processed by the circuit, results latched into the next stage's input register on the next clock cycle.
The source is an example for AIB plus psi. Looks like registers R1, R5, and multiplier or adder circuits.
Yeah, it shows how data for different calculations flows through. Input AI, byte to R1, R2, segment 1 multiplies them, result to R3, input C to R4, segment 2 adds R3 and R4, result to R5. It takes a few cycles to fill the pipe, but then the results come out steadily.
Like getting the assembly line up to speed, and the space-time diagram visualizes it.
Exactly. It plots time, clock cycles horizontally, and the pipeline segments vertically. You can draw diagonal lines showing each task, T1, T2, etc., moving through segments S1, S2, S3, S4 over time.
And you see the overlap clearly. T1 takes, say, 4 cycles to finish, but T2 finishes at cycle 5, T3 at cycle 6, and so on.
Right. After the initial K cycles to fill a K-segment pipeline, you ideally get one result per cycle.
Which leads to pipeline speedup. How much faster is it?
The formula given is speed up S, time non-pipelined. Time pipeline, that's NTN, K plus N1 TP.
N tasks, TN time per task, non-pipeline, K segments, TP pipeline, clock cycle time.
Okay. For many tasks, N much larger than K, this simplifies. The K1 part becomes negligible. It approaches NTN, NTP, which is TNTP.
So the speedup is roughly the ratio of the time per task without pipelining to the pipeline's clock period.
Yes. And if the logic can be perfectly divided such that TN equals KTP, total task time equals K segments times the time per segment, then the ideal speedup is K.
A K-segment pipeline gives up to K times speedup. Sounds great.
It is great, but the ideal K is often hard to achieve in practice due to the various issues we'll get to.
Okay. Before the problems, what kinds of pipelines are there? The source classifies them.
3 main types mentioned. Arithmetic pipelining, segmenting complex arithmetic operations like floating point add or multiply, common in high-speed math units.
2.
Instruction pipelining, the one we've mostly discussed, overlapping fetch, decode, execute, etc., of the instruction stream itself. The most common type in CPUs.
3.
Processor pipelining. Less common maybe, but where you chain multiple processors together, each doing one step of a larger task on a stream of data.
Focusing on arithmetic pipelines, the floating point add-subtract example seems detailed.
It is. It shows a practical application. You have 2 normalized inputs, x, a to a, and y equals b to b.
4 segments are needed.
Yes. Segment 1. Compare exponents, a and b, to find the difference. Segment 2. Align mantisses, shift the mantissa of the number with the smaller exponent right by the difference calculated in segment 1.
So their effective exponents match. Then segment 3.
Add or subtract the aligned mantisses, a and b. Segment 4. Normalize the result. If the sum difference is too large or small, shift the resulting mantissa and adjust its exponent accordingly.
Makes sense. Breaking down a complex operation. Now, back to instruction pipelining.
Right. Overlapping instruction phases. The source mentions a simple 2-stage fetch-execute pipeline with a FIFO buffer.
First in, first out. So instructions queue up after fetching.
Yes, it helps smooth out the flow between fetching and execution.
Hmm.
But a more typical model is the 4-segment pipeline. FI, fetch instruction, DA, decode and calculate address, FO, fetch operand, EX, execute.
FIDA, FOEX.
Okay. A key assumption here for efficiency is often having separate memory access paths for instructions and data.
Why separate?
So the FI stage can fetch the next instruction from instruction memory at the same time as the FO stage fetches data operands from data memory for an earlier instruction already in the pipeline. Avoids a bottleneck.
Prevents them from fighting over the same memory bus. Good point.
But even with that, things aren't always smooth. We run into pipeline conflicts or hazards.
The problems that reduce that ideal speedup.
Exactly. 3 main types. First, resource conflicts.
Like needing the same hardware piece at the same time?
Yes. The memory example is classic. Even with separate caches, maybe 2 stages need the same adder or functional unit simultaneously. Requires careful design or sometimes stalling.
Second hazard type.
Data dependency or data hazards is a big one. An instruction needs a result from a previous instruction that hasn't finished yet.
Like add R1, R2, R3, R1 equals R2 plus R3, followed immediately by sub R4, R1, R5, R4 equals R1, R5. The subtract needs the new value of R1 from the add.
Perfect example. The sub instruction enters the pipeline right after add, but when sub reaches the stage where it needs R1, the add might still be calculating it or hasn't written it back yet. The pipeline has to wait or stall.
Unless we can fix it somehow. We'll get to fixes. What's the third hazard?
Branch difficulty or control hazards. Caused by branches, jumps, calls, anything that changes the program counter, PC, unexpectedly.
Because the pipeline is happily fetching instructions sequentially, PC, PC plus 1, PC plus 2, but a branch might suddenly say, nope, go to address X instead.
Exactly. The instructions already fetched after the branch, PC plus 1, PC plus 2, might be wrong if the branch is taken. They have to be flushed out. And the pipeline restarted from the branch target address. Wasted cycles.
Okay, hazards identified. Now, detection and resolution. How do we handle data hazards like that R1 dependency?
A key hardware technique is operand forwarding or bypassing.
Forwarding sounds helpful.
It is. Instead of waiting for the add instruction to finish executing and write R1 back to the register file, the hardware can detect the dependency. If the ALU has just computed the new R1 value for the add, it can forward that result directly to the input of the ALU stage for the sub-instruction, bypassing the register file, write and read.
Like a shortcut for the data, avoids the stall.
Often, yes. It significantly reduces stalls caused by many common data dependencies.
Can software help too? The compiler?
Yes. If forwarding is impossible or doesn't fully solve it, the compiler can insert NOP, no operation instructions.
Just do nothing for a cycle.
Pretty much. It creates a bubble in the pipeline, delaying the dependent instruction, sub in our example, until the needed data R1 is ready.
Or the compiler could reorder instructions.
That's smarter if possible. If there's another independent instruction that can be moved into the slot after add but before sub, the compiler can reschedule the code to fill that potential stall cycle with useful work.
Clever. What about side effects?
Yeah. Some instructions change things implicitly, like condition code flags, zero flag, carry flag, etc. If add R1, R2, R3 sets the carry flag, and the next instruction is add with carry R4, R5, R6, that second instruction depends on the side effect, the carry flag, of the first. Pipeline designs need to handle these implicit dependencies carefully. Often, modern instruction sets try to minimize such side effects.
Okay, that covers data hazards. Now, the branch hazards, the instruction hazards, unconditional branches first, they still cause issues.
They do. Even though you know where you're going, by the time the branch is decoded, the pipeline has likely already fetched the instruction after the branch. That fetch was wasted work. This delay is the branch penalty.
Can we reduce it?
By calculating the target address and fetching from there earlier in the pipeline if possible. Also, instruction queues and prefetching help generally. Fetching instructions ahead of time into a buffer can hide some memory latency and keep the pipeline fed, potentially reducing the impact of stalls, including branch penalties.
Makes sense. But conditional branches are worse, right? Because you don't even know if you're branching until later.
Exactly. The decision, branch taken, not taken, often depends on a result from a previous instruction's execution, like comparing two registers. So the pipeline is flying blind for a few cycles, and the source node's branches are common, like 20% of instructions.
So how do we handle them? One I mentioned is delayed branch.
Right. This is a software-hardware coordinated approach.
Right.
The rule is the instruction immediately following the branch instruction in the delay slot is always executed, regardless of whether the branch is taken or not.
Always. That sounds risky.
It requires the compiler to be smart. The compiler tries to find an instruction that can be safely moved into that delay slot. Ideally, an instruction that was originally before the branch and doesn't affect the branch condition, or sometimes an instruction from the target path if it's useful whether the branch is taken or not.
How often can the compiler find a useful instruction?
Depends on the code. If it can, it avoids a stall cycle. If not, it has to put a NOP in the delay slot and you still have the penalty.
Okay, delayed branch is one approach. What else?
Branch prediction. This is huge in modern CPUs. Try to guess the outcome of the branch early.
Guess. How?
Simplest form. Always
No.
predict branch not taken. Just keep fetching sequentially. If you're right, branch isn't taken, great, no penalty.
But if you're wrong, branch is taken.
Then you've fetched and possibly started executing the wrong instructions. You have to flush them, squash their results. This relates to speculative execution, executing based on a prediction, and start fetching from the correct target address. So there's still a penalty on a misprediction.
Can we predict better?
Yes. Static prediction uses simple rules, maybe based on branch direction. Backward branches often loop, so predict taken. Forward branches often skip, so predict not taken. Or the compiler adds a hint bit.
And dynamic prediction.
That's more complex hardware. It keeps a history table for recent branches. If a branch was taken the last few times it executed, predict it will be taken again. Much more accurate, but more hardware.
Wow. So handling branches is really intricate.
It absolutely is. Minimizing that branch penalty is critical for pipeline performance.
Okay, well, that was definitely a deep dive. We went from basic multiplication unsigned, signed with sign extension, Booth's algorithm,
Through restoring division.
and then into the whole world of pipelining the basic idea. Arithmetic versus instruction pipes, the hazards resource, data control.
And the techniques to deal with them, like forwarding, NOPs, delayed branching, and prediction. It really covers the fundamentals of how processors crunch numbers and execute instructions efficiently.
It feels like we've crammed for that final exam and hopefully nailed the key concepts. Understanding this really gives you a new appreciation for what's happening under the hood.
Absolutely. These aren't just abstract ideas. They're the core techniques that make modern computing possible.
So, thinking about all these trade-offs, hardware complexity versus time, the challenges of hazards, here's a final thought to chew on. In modern processor design, what do you think is the most critical balancing act for engineers? Is it squeezing out every last drop of parallel execution? Is it minimizing power consumption by keeping hardware simpler? Or is it something else entirely, like managing the complexity of predicting branches accurately?
That's the multi-billion-dollar question, isn't it?
Yeah.
There's probably no single right answer. It depends heavily on the target application, high-performance server, mobile phone, embedded controller. But finding that optimal balance is the core challenge.
Definitely something to think about.